Okay, guys, today, after talking about angles that are formed by tangents and secants and chords, now we're going to talk about segment lengths and how you can find segment lengths as they relate to circles and tangents, chords, and secants as well. Again, I'm not going to do the proof of these theorems. They do have a lot to do with similar triangles, creating similar triangles, drawing some auxiliary lines in, creating similar triangles, and setting up proportions. That's how where a lot of the theorems in this particular section are going to come from, but you're not going to see the proof of these theorems. If you would like some assistance on guidance into where you can see the proof of theorems, then let me know and we can talk about that a little bit. Either I can prove them for you, or if you wish, I can direct you to some other places on the internet where you can find the proof of those. So the first theorem we're going to talk about is that when you have two chords intersecting inside a circle, and when you have two chords that intersect inside a circle, then obviously they divide each other at that point of intersection. It doesn't mean that that's the center of the circle, but it is the point of intersection. So it splits each of those chords into two segments. And when you split each of those chords into two segments, you get this of length A and this of length B from this chord that you can see in red. And then you also get this length C in blue and this length D in blue. Okay, and then when they intersect inside a circle, the product of the segments of one chord is equal to the product of the segments of the other chord. And really what that means is that means that A times B is equal to C times D. And that's pretty much how you would set it up anytime you're looking to find one of those partial segments inside. Don't assume that things are congruent. Don't assume that things add up to be the same thing. And remember that you could have things like, remember that 4 times 3 is 12 and 6 times 2 is 12, but they don't add to be the same length, right? So you could, in essence, say that A is 4. We could say, let's just pretend, we could say, okay, well, A is 4 and B is 3. And C is 2 and D is 6. I know that that doesn't make great sense, but the product is the same. The product is still 12. 4 times 3 is 12. 2 times 6 is 12. But they definitely don't add up to be the same thing. And that's just an example of what we're talking about when we talk about these two products being equal in a sense. And then we're going to talk about another theorem where you have two intersecting secants. When two secant segments of a circle intersect at a point outside the circle, and that point outside the circle would be point P in this case, then the external piece of one segment, and we're going to say that that's W, the external piece of one segment times the whole entire secant segment, which would be x, not xw, not x times w. But remember that would be x plus w, is going to be equal to the external piece of the other secant segment times the whole entire secant segment right here. So this would be z plus y, and this one would be x plus w, right? Okay, and that would look something like this. W times w plus x, the external times the whole secant segment, is going to be equal to the external times the whole secant segment. So I do like to write that, the external, I like to write it in words. I think it's a good idea for you to write it in words. External secant segment times the whole secant segment, and that comes from the point that's outside the circle all the way to the farthest point intersecting the circle, is equal to the other external secant segment times the whole secant segment. Okay, and if you want to label them as, you know, external secant 1, external and whole secant 1, then you can do that however you wish. But I do think it's a good idea for you to say the words, write the words before plugging everything in, and be mindful of the fact that when you want to get the entire secant segment, you have to add the parts that are collinear together, okay, like segment addition postulate. All right, and the last theorem is when a tangent segment and a secant segment of a circle intersect at a point outside the circle, like P again, then the square of the length of the tangent secant segment is equal to the external. So here's the square. Let's talk about the tangent segment. Remember the tangent segment intersects the circle at exactly 1 point. So that length, t squared, is going to be equal to the external secant segment of the secant y times the whole secant segment, and that would be z plus y, right? So that one looks something like this, and I do still think it's a good idea for you to express that in words as much as possible and say the tangent segment squared is equal to the external, let's not forget the n, secant segment times the whole secant segment. And you can use whatever variables you choose, or if you have points, I do think it's definitely better to use points. Now let's see what it looks like when we try to apply those theorems. Okay, so you may want to have that in front of you, maybe look at that one, this one single page of notes a little bit to help you with solving some of these problems. All right, we're going to find the value of the variable. If the answer is not a whole number, we're going to round to the nearest tenth. Let's express it as exact, and then also we can round it as well. All right, so I'm looking at the picture for A, and I notice that we have two secants. Remember that we have two secants in this case, right? We have a secant here, and we have a secant here, and these two secants do intersect at a common point outside the circle, right? So let's look at the fact that we have an external piece right here, right there, and then we have the whole secant segment. And then we also have an external piece here, which is 7. And then we have the whole piece, which is going to be 7 plus y. So don't forget to add carefully a little bit, okay? All right, so we're going to say 6 times 6 plus 8 is equivalent to 7 times 7 plus y. We're definitely not going to distribute the 6. We're going to go ahead and add that and get 14. And 6 times 14 should be 84. Now we're going to distribute the 7 because we can't add the 7 and the y first. So we get 49 plus 7y. 49 plus 7y. So now we have 7y is equal to, and we're going to subtract 49, and we get 35 is equal to 7y, and then y is equal to 5, and you're done. Found the value of y. It was an exact value, so we didn't have to approximate it all. All right, let's take a look at the next picture. And always think about what are you looking at so that you'll know what theorem to apply. So now we see in this picture for B, we have an external secant, right? We have an external an external tangent. We have an external tangent, that's Z. So we're just going to go ahead and label that as a tangent, right? And then we have an external piece of a secant segment, external, and then we have a whole piece right here, whole secant segment. It's a good idea to label everything as best you can. Okay, and remember that the theorem from the previous page says that a tangent segment squared is equal to the external secant segment times the whole secant segment. So when we plug in what we have, we've got z squared is equal to the external piece is 8. But then the whole piece is going to be 16 plus 8. So let's not forget to go ahead and add that together. And 16 and 8 is going to be 24. And 24 times 8 is going to be 192. So z squared is equal to 192. 192 is not a perfect square. So you could break that down. Definitely you could break that down if you choose to do so. But since we're already asked to just round it to the nearest tenth, let's just go ahead and take the square root of 192. And that's approximately 13.8. And now you've got the value of z. And if you were going to break down the 192, Remember that that could be 8 times 24, which is what we had started with. And this could be 8 times 3. So we have 2 8s, and you don't need to go further. If you were going to write this as an exact form, you would say that c is equal to 8 square root of 3. That would be an exact answer, even though you weren't asked for that. And this one is an approximate 13.8, right? All right, let's do a couple more before you try something a little more challenging. Okay. All right, let's take a look at C, and let's think about what we've got. We've got segments. We've got chords forming parts of segments. So remember, again, when we look at the previous note of pages, the previous page of notes, we have the product of these two parts of one chord. 3 times x is going to be equal to the product of the two parts of the other chord, 12 times 2. So 3 times x is equal to 12 times 2. So 3x is equal to 24, and x is equal to 8. Again, notice that doesn't mean that the chords are the same length. It means the product are the same. Product is the same. All right, one more time, same exact thing all over again. We have two chords intersecting inside a circle, and each chord gets split into two parts, the product of which is equal to each other, right? So that means that 3x times x is going to be equal to 6 times 8. So then we have 3x squared is equal to 48, x squared is equal to 16, and x is equal to 4. Good. Okay. Let's try a couple that are a little bit more challenging, I think. We'll see. Probably not much for you, but we'll give it a try. Again, it's a good idea for you to kind of pause, try to do these on your own as much as possible, hit pause, and then go back and check and see if you're getting them right. So we want to find the values of x and y. We've got a lot going on in this picture. I look at this picture and I see a few things. I see a tangent, right? Here's a tangent. Ugh. We're going to have to use the regular pen because that won't go straight. But we have a tangent segment, so let's take a look at that. Tangent segment. We have an external secant right here. External, let's say it's external 1, and let's say this is external 2. The 3 is that external 2 right there. Okay, and so then we have this whole entire piece, whole, and we'll give that a subscript of 1, and we could say this whole entire piece would be whole secant subscript of 2, right? So it's kind of hard to say what we really should figure out first. Definitely looks like we could set up a couple of different things. So let's just see what it looks like when we set up a few different things. We know a couple of things. We know that the tangent segment squared is equal to the external secant segment times the whole secant segment. So, well, which one should we use? It really shouldn't matter which one we use. If we set up the tangent segment with y, so if we say y, which is the tangent segment squared, is equal to, and then let's say we use the closest. Let's say we use the closest secant, and that closest secant is actually the 3 and the x. So this is the closest one to that. So let's say we set it up like that. The external secant segment, 3, times the whole secant, which would be x plus 3. Well, what's going to happen in this case? We can't solve it all the way because we have two variables. So the fact that we have two variables, and we don't have a system, we can't solve it just yet. We could probably use a system, but it's not a good idea. Let's try to set this up a different way. So let's try a different way a little bit. So that's no bueno, right? We're going to try to set it up a little bit differently. So let's try this one. Let's see if we set it up as y squared equals, now let's try this one. 4 times the whole secant segment, 4 plus 5. That'll work a little bit easier, okay? So then we get y squared is equal to 4 times 9, y squared is equal to 36, and y is equal to 6. And then we're done. And then if you'd like to go back and use that in this other equation, then there's no harm, no foul. We could use that all over again. So let's take a look at what that would be if we just clone all this. And bring it over here. Now we could just plug in. Now we can just plug in this 6 right here if you'd like. So we could say 6 squared equals 3x plus 9. This will be another way for us to find the value of x. So 36 is equal to 3x plus 9. 3x is equal to 27, and x is equal to 9. And that's a way for us to find it instead. Now, if you prefer to use the two secant segments, you definitely could have done that. So you could have set up something a little bit different, right, to find the value of x. And it's not necessary, but you could have said 4 times 4 plus 5 is equal to 3 times 3 plus x, and that should still give you the exact same answer, right? This is going to give you the same result. It's not going to be any different. All right, let's try something a little bit more challenging. Okay, we know the length of PB is equal to the length of AB, which is 5, and the length of PD is 4, and we want to find the length of PT and the length of PC. Remember that pictures are not drawn to scale. I'm never going to draw pictures to scale, but let's put all the information in here. We know the length of PB is equal to the length of AB, so that's 5. This is also 5, and we know the length of PD is 4. Let's just make this a little more clear right here. Hard to see that. And the length of PD is 4. And we want to find the length of PC and the length of PT, right? So let's put a question mark on those. Here's PT. And what type of segment is PT? Segment PT is a tangent segment, right? This is a tangent segment. And a tangent segment squared, if you'd like to try to use that one first. Then a tangent segment squared is equal to, remember, an external secant segment times the whole secant segment. So we do want to find the length of PT, and I'm just going to leave that as PT. That is the variable that it's understood to be. So PT squared, and it really shouldn't matter which one you use, but since we don't know the length of PC and we also have to find that, how about if we go ahead and use the one that we have? We have this 5, PB, that's an external, times the whole entire thing. And how much is the whole secant? That's always the hard part, is remembering that we have to do the whole secant, right, which is the length of AP. So the external part is 5, but the whole entire secant, PA, right, this is PA, this is going to be 10. 5 plus 5. Got it? So PT squared is equal to 50. Now let's take the square root of each of those. I'm going to express this answer in exact form because it didn't really say. So PT is equal to 5 square root of 2. Remember, if you need to, break down and put it in simplest radical form. Make a factor tree of some sort. If you prefer to use your calculator, then you can just approximate it by typing in the square root of 50. All right, now let's find the length of PC. What is PC? So we have an external piece here, but then PC is a whole secant segment, right? Okay, so we can either use PT if you wish, which is fine, or we can use PA. I'm going to go ahead and use PA because I know that information, and if I got PT wrong, I don't want to make the same mistake again. So remember that we can say that the external secant segment times the whole secant segment is going to be equal to the external secant segment times the whole secant segment if we have two different secant segments, right? So I'm going to use those, and I'm going to go ahead and label everything for you so that you know what I'm talking about. The external secant segment in blue that I'm talking about is segment PD. The length of PD times the whole entire thing, the length of PC, is equal to the other external secant segment, which is PB, times the length of the whole thing, which is PA. So PD is 4 times PC, which is something that's unknown. Again, that's something that we're solving for, is equal to the external secant segment PB, which is 5, times the whole length of PA, which is 10, right? So we can say that 4 times PC is equal to 50. PC is equal to, we divide by 4 and reduce, and we get 25 over 2. Or if you want to write 12.5, that's okay. You know I prefer the 25 over 2 in pure mathematics. We're going to use improper fractions a lot more. And that's it. Remember that that has to do with segment lengths, not with angle measures, but with segment lengths that are formed by chords and tangents and secants. And you're going to need both of those things for upcoming homework assignments. And that's the end of that one.